An interesting example of a diffraction grating is something that is some of our technology that's becoming a little bit ancient, but it's not even designed to be a diffraction grating. What I'm talking about is a compact disc, because it consists of rows of pits that are so small and close together that even with respect to the wavelength of light, they look comparable in size. In other words, they're small enough that they produce interference patterns for light that is very visible. Now they're designed to pick up the information based on the spacing of the pits. So here's a micrograph of part of a CD, and you see these pits along here, and there's many rows of them. As the CD spins around, the laser beam is shining on these things and interpreting where the pits are and the other areas are called the lands, and it basically gets digital information from that. So here's zeros, here's 1 at the transition, 0, 1, 0. So it's digital information that is being picked off the CD as a result of the spacing of the pits. And so that's kind of interesting. So here's another visual. So you see all these rows of pits as it spins around. And a low power laser beam is picking up the information, whether it's a pit or a land, a raised area, or a depressed area, or a raised area, depending on how you look at it, for the pit, and not so for the land. The description here is a little simplistic, but nevertheless, if you're writing to the CD, then you're actually burning areas. You're burning pits into the substrate itself. So it's pretty ingenious. It's pretty awesome, and a lot of information can be picked up off a CD or stored on a CD, as probably everybody already knows. You probably all had some experience with them. And so let's look at this a little bit more and see how these CDs act as diffraction gratings, which again, they're not designed to, but because of the fact that you've got rows of these next to each other, they can produce interference patterns like a multiple slit device that's designed to be a diffraction grating. So just a little bit more about what the light is doing in a little more detail. So you have a light from a laser beam represented as waves here. And you got the pit, and there's a different path length to the pit than there is to the land. All right, and so this is actually, say, a quarter wavelength more. So a quarter wavelength twice over, when it reflects off of this, has to travel. Let's look at it on this side. Has to travel. Okay, a quarter plus a quarter is a half a wavelength. So the reflected ray, basically, here's the reflected ray from the land, here's the reflected ray from the pit. And you'll see that based on the color of the light, the depth of the height of the pit, depth of the pit, however you want to look at it, is a quarter wavelength. So it's a half wavelength difference, so there's cancellation of the light. So you have light and dark happens really rapidly. And that's what this sensor picks up and interprets as the digital information. Isn't that ingenious? Isn't that cool? And I'm kind of using this as an illustration as well, because in our next topic is going to be about, very shortly at least, we're going to be discussing thin films. And the same kind of principle happens when you put oil on water and you see pretty colors. It's the same kind of principle. You got cancellation in certain places, certain wavelengths, because of this path difference. So anyway, the ray that reflects off of here has traveled 2 times the thickness, which is a half a wavelength further, and that causes this phenomena of the cancellation. So I just want to describe it a little bit more. So on a CD to a DVD to a Blu-ray, you got higher resolution, right? And you really do, because in a CD what you're doing is going toward ever increasing quality of lasers, I guess you'd say, or reduction in the wavelength. So with a higher wavelength, like infrared lasers at times with a CD, gives you a pretty big region here. Now, a big region doesn't lend itself to high resolution. A smaller dot, a smaller spatial region, will produce higher resolution or more information on a given medium. And I will now explain why. So, the reason why is because here we have a CD, DVD, Blu-ray, all right? So the CD, you see that everything is larger. It's the pits are wider and thick, have a greater width and greater depth, if you will, in these two dimensions, all right? And as we go to DVD, you notice them all smaller and even smallest with the Blu-ray. Likewise, the spacing between the pits, the spacing is getting smaller and smaller. Then the distance between the rows is getting smaller and smaller. So the information density on a Blu-ray is much, much greater than a CD or even a DVD. And the reason you can do that is because, Blu-ray, what's a Blu-ray? Well, it's got a blue or even violet laser beam, which is a much shorter wavelength. Shorter wavelength produces a smaller region where it's putting its energy, its light energy. And so if you put this size of laser spread in this kind of information, you'd be covering all kinds of pits and lands, and it'd just be a mess. You wouldn't be able to pick up the information. You can't have this region interfering with the other ones inappropriately. It's got to pick up the information, the duration of these pits, the spacing in between them to get the digital information. So now you can see why Blu-ray is so much more able to store lots of information, okay? And you get the HD quality because that is associated with a lot of data. And also the depth, the reading depth is diminishing as well as you go from CD to DVD to Blu-ray. Okay, and now to describe the function of the CD that it's not designed for, which is producing these beautiful rainbow colors. Look at how pretty that is. Maybe they should just make the CD so we can observe the colors of the rainbow. Well, you're equipped now to understand why that's happening, because the CD is like a diffraction grating as well, where you got these, rows of pits and non-pits. The non-pits are lands. And, you've got the spacing between these, the spacing. And this can be thought of as slits. You have slits where the light energy is, and if you shine a laser beam on these, okay, you get reflection, and in the reflection, the light interferes. So it's not a transmission diffraction grating, it's a reflection, but the principle is exactly the same. So in the reflection, you have, if you think of each one of these pits now as a source of light, all right, a source of light, then it's producing rays that come here, and at the right distance from the screen, like we've seen before, the path difference is going to be lambda, right? So there's lambda, and it's only going to be lambda at the right region here for a particular color. And at lambda, we're going to get a bright spot, right? And so, now remember the relationship, lambda over d is equal to y over d. This is not going to work for a diffraction grating, a CD diffraction grating. And the reason why is because the spacing, okay, normally this angle is real small, but in this case it turns out that this angle is going to be large even for the first order, right? Even where you got a bright spot in the after the large central bright spot. So sine of theta is not equal to tangent of theta. And if it is, that's where we get this situation. So d sine of theta is m lambda. We need to use that explicitly. We don't use this approximate form which worked for the two slit. Okay, we can't do that now. So, and the interference maximums, they're going to occur for different colors. They have different wavelengths, so they're going to be at different angles. There's different angles for each color, right? So for a shorter wavelength, it's going to occur with less distance, a smaller angle. Well, if you think about it, as you just look at this, representation, whatever from your perspective, you're seeing the different colors at different angles along here. See, blue, green, yellow, red, etc. So it's based on the locations where you actually have the interference going on. So that's pretty cool. So you can imagine that if you knew the wavelength of the light, you might be able to figure out D, the separation of the pits, of the rows of pits on a CD, by having the rest of this information. And in fact, some of you, if you're in my class, which is probably most of you, will actually do this in an activity. So you're going to actually figure out the spacing between these pits. So that's a good example of getting used to the various parameters of a diffraction grating. And with that, we will close out this lesson and catch you next time.